So this is the first in a series of screencasts on the subject of acids and bases for the module CHE10063. I'm Martin, and so welcome to the first sort of the topic based screencast, so the content based screencasts for this topic. So basically what we're going to do now is we're going to talk a brief introduction to acids and bases first and foremost, and also talk a little bit about equilibrium chemistry of these things. Okay, as I said already, I'm going to be putting QR codes throughout the slides, and these will take you to the bibliu.com website and to the specific page numbers that are listed on the slides. So when thinking about what constitutes an acid or a base, historically, the first thing that would have been noted was that acids, for example, are tasting quite sour. So that's here. And indeed, when you get a base on your hands, or historically people would have got some base on their hands and they would have felt that it feels soapy. And the reason for that is the reaction that we've outlined here. The fat on your fingers is reacting with, for example, in this case, NaOH to produce glycerol, and actually you'll be doing this in biodiesel later in the semester, albeit with not quite NaOH. You'll use NaOH plus methanol, and the product won't be sodium stearate but biodiesel. But the product of this reaction here is sodium stearate, which is a soap, okay, and that's why your hands feel soapy if you get a bit of NaOH solution on it. Of course, these historical definitions, these historical observations, aren't ideal in terms of chemistry, first and foremost because, obviously touching and tasting things is hazardous potentially, but also because we can't really quantify them. But nevertheless, it's always worth remembering that these are the case. And often, you'll find, for example, if you sniff or if you smell an acid in a lab, often by accident, you'll get a very sort of acrid, sour, feeling or taste. Okay, and that's one of the ways of determining whether something's acidic or not. Okay, but looking at more scientific definitions, the first person to really start to define acids or bases was this person Arrhenius, and he basically looked at salt and water and said that neither of those two things will conduct by themselves, but when you put them together, when you mix salt into water, when you dissolve salt in water, for example, as a solution of NaCl, that resulting solution will actually conduct water. And he proposed that was because the salt was essentially dissociating to give ions effectively. Now, applied to acids and bases, he essentially said that an acid he defined as something that will react with water and produce the ion H3O+. And of course, he was right about that. And equally, he said for a base, it will react with water to produce OH-. So Arrhenius actually got quite close to the next type of acids that we're going to talk about on the next slide, the Brønsted-Lowry definition, because he really did prioritize the hydrogen species. Okay, but in his case, he focused on water as a solvent, and of course that's not the only thing we can have. But under Arrhenius's definition, you could have direct production, so that would be NaOH. You could just literally go, well, NaOH is going to just dissociate by itself, so NaOH is going to dissociate, and it's going to be in equilibrium, although this equilibrium will be heavily to the right hand side, in water to form Na plus Aq and OH-, and of course it's the OH- that he would have required for it to be a base, so therefore it's a base because of the OH-. Equally, in indirect production via reaction with water, so H2O plus NH3, and we need some state symbols here, don't we? Again, this would be a gas in this case, in equilibrium with NH4 plus now Aq plus OH-, again Aq. Okay, so two different types of production, both of which would give acids and bases under Arrhenius's definition. And again, the requirement for water is the important point here. Okay, so moving on to a bit more of a general definition, Brønsted and Lowry essentially came up with the idea that an acid is a proton donor. So for example, in the reaction here, HCl go plus H2O to H2O, so plus water. The HCl is going to donate a proton to the water molecule to make H3O plus and leave the chloride ion as a sort of a counter ion. Okay, so this would still fill Arrhenius's definition, but it puts the point onto the protons now. Okay, and equally a base will be a proton acceptor, so water plus ammonia in exactly the same way as before is going to react, but the water is going to donate a proton to the ammonia to make NH4 plus, and you're going to make OH minus in this case. Okay. The key point here is it removes the need for water, so it allows for acid-base reactions to take place outside of water, but that still involve hydrogen. So, for example, here you've got two gases mixing to yield two solids, or two solid ions. Could easily be in water, but doesn't have to be. And equally here, you've got a situation that could either occur in ammonia, if it were a liquid form, or could occur in this here. Okay. So you don't necessarily need water anymore under the Brønsted-Lowry definition. It's all about protons. Okay, so let's talk about Brønsted acids a little more generally, and we're going to just talk about a generic acid which has a hydrogen and its conjugate species dissolving in water. Okay, so this A could be Cl, for example, in the case of HCl. This dissolving in water, you get HA, and that's going to give us our H3O plus and our A minus. Obviously, if this was the case for HCl, this A minus would be Cl minus. Generally speaking, by the way, throughout these notes, I'm going to be talking more generally about a generic acid HA than I will about specific cases. And one of the things you need to be able to do in this course is relate the general cases back to the specific cases. Okay. Anyway, we've got an equilibrium here, and of course, if we've got an equilibrium, we can write an equilibrium constant for that equilibrium, and also that equilibrium constant has an equation that's associated with it. So we can write Ka is equal to, and it's basically the products on the top. So in this case, it's concentration of H3O plus multiplied by the concentration of A minus, and that's going to be over the reactants. Okay, and in this case we only need to consider the concentration of HA. Right, why do we not put H2O in there? It's because in an equilibrium constant expression, we consider the activity, or indeed the concentration in this case, of a liquid, so the actual solvent in this case, because it's water as the solvent, there's a lot of it. We consider the activity of that to be 1 mole per decimeter cubed. So effectively you're dividing by 1 to get that. Okay. We can do the same thing for a base dissolving in water. Now in this course we're mainly going to be focusing on acid strength, acid equilibria, and so we're going to mainly focus on Ka, but one thing you need to remember is that every time you can write Ka, you can also write a Kb. Okay, so in this case we've got a base dissolving in water, and just as if we had NaOH, we're going to get the base is going to pick up a proton from the water and leave our OH minus ions, and the base is going to get that proton. It's going to accept the proton, and again we can write out a constant, an expression for Kb, which is again it's the products, so BH plus OH minus over the concentration of our base in water. Okay, and again we don't include water because it's the solvent and it's got an activity of 1. Okay, so key point of definition is that Ka, so it's this equilibrium constant with a subscript A, this is the acid dissociation constant, and for Kb that's the base dissociation constant. Okay, so just a bit of an aside here, which just to make a couple of points clear. We've written an expression for the acid dissociation constant, Ka, and I've used concentrations. Okay, now obviously if these concentrations cancel, you'd have this one in molar, this one in molar, and that in molar, and that would effectively give us units of Ka of molar. Now, that's not actually true, okay? Ka has no units. Thermodynamic Ka has no units, as noted there, and you're going to learn a bit more about that with Dave McGarvey next semester. Now, the reason for this and the way we sort of actually think about this in the equilibrium formula is that actually the reality is that we measure the concentration of acid, aqueous concentration of acid, and before we put it into this formula we divide that by 1 mole per decimeter cubed. So it's a bit like a mathematical trick to get to sort out the units, but the same thing applies to A minus and HA, but that's basically why the units of Ka don't exist, but yet we do have units for all of these individual things. So that's an important thing to remember, and something that if you try to do unit tracking for this, it's not quite so obvious unless you remember that point. Okay. The other issue is that actually strictly, and if you look at elements of physical chemistry, it points this out very clearly, strictly the Kas, or indeed any equilibrium constants, should be written using activities, and you'll learn more about that in year 2. Okay. We're not dealing with that now. Okay, so what we're going to do is basically approximate activities to be equal to concentration. So effectively what we're doing is we're saying the activity of H3O plus is approximately equal to the concentration of H3O plus, and we're going to do that for all of the species. And that's a reasonable approximation, under dilute conditions. Okay, so that's the sort of conditions we're going to be dealing with in this course anyway. So it's fine to make that approximation. Okay, so getting back to the main content, we have a bit more terminology here. So again, we have our generic acid HA reacting with water to give H3O plus A minus. Okay, the conjugate base of the acid is this A minus. So this is referred to as the conjugate base of the acid. Okay, so again, in the example of HCl plus water goes to H3O plus Cl minus, the conjugate base would be Cl minus. Okay, but equally you can have a conjugate base of many other different types of conjugate base. Okay, the conjugate acid of a base is the sort of same thing. So in this case you've got the generic base reacting with water to give our conjugate base of the acid plus our OH minus ion. Okay, now key point about these is that either of these species might react again with water. Okay, and so if they do, what you get is the following. So for example, A minus might react with water. Yep, and that's going to be liquid, is going to be in equilibrium with AH, so it picks up a proton again, plus OH minus. Yeah, so that reforms the sort of HA or AH, and of course that's got its own constant, but in this case, because it's reacting with water and it's water's donating a proton, then the A is behaving like a base, so this is a Kb. So Kb is equal to concentration of AH, concentration of OH minus over concentration of A minus. And you can do the same thing for the conjugate acid of a base. So this would be the Kb for the conjugate base of the acid. You do the same thing for the Ka for the conjugate acid of the base. So again, you've got BH plus AQ. Oh, I've missed out a couple of state symbols on the first equation. Let's put them in. BH plus AQ plus H2O is in equilibrium with B. Again, so it reforms the base plus H3O plus. Okay, so this is behaving obviously as an acid here because it's a conjugate acid. Okay, and again you can write out the equilibrium constant, and so it's Ka because it's behaving as an acid, and it's concentration of B, concentration of H3O plus over concentration of BH plus. And again, we don't have the H2O in these equations for the same reasons we said before. The activity or the concentration of those are regarded as equal to 1. Okay. All right. So yeah, this is the Ka. So these will become important in a second. Okay. So we have to make a slight sidestep here and think about water. Okay. Kw is talking about the constant or the equilibrium constant of water reacting with water to form dissociated species. Okay, and the reason water can do that is because it's amphiprotic. It can donate or accept a proton. Okay, so you can get this kind of equilibrium built up. So water, add water, goes to H3O plus OH minus. Okay, and that's got the equilibrium constant for that process is Kw, and that's the equilibrium constant in the sort of right direction. Okay. The value of that equilibrium constant is 1 times 10 to the minus 14. Now, this is quite an important value, and this is actually going to give you your pH scale, and we'll talk about that in a later screencast. Okay, and of course that applies at sort of room temperature. But the value of this constant is just going to be the concentration of products, right? So it's just the products. We're not dividing it by anything because the activities or indeed the concentrations of H2O are equal to 1, okay? And the key point about this is that Kw stays fixed, okay? So if you increase the amount of H3O plus, then you will have to therefore decrease the amount of OH minus in order for Kw to stay fixed, okay? And it also means that if you know the concentration of H3O plus, then you can calculate the concentration of OH minus, of course, okay? And again, as I said already, this gives us our pH scale in water. Now, let's just pull all this together, Kw and acid strength. So the key concept here is that the strength of an acid, and we're going to talk more about the strength of an acid in the next screencast, but the strength of an acid HA or AH is going to be linked to how strong its conjugate base is, and the same applies to bases, okay? So, you know, what we can do is we can basically derive this equation here, and they're going to be linked through Kw, okay? So let's just do that quickly. So let's write out for an acid, for example. We've got Ka for acid A. Okay, so Ka will be equal to concentration of H3O plus concentration of A minus over concentration of AH, yeah? And this can be HA or AH. I know I've flipped them around on previous slides, it doesn't matter. We've got Kb for the conjugate acid, conjugate base, sorry. Conjugate base A minus, so that's the conjugate base of the acid AH, and that is given by Kb is equal to concentration of AH, concentration of OH minus over concentration of A minus, and these equations are just from the previous slide, right? Okay, and okay, let's see what happens if we multiply these two together, because obviously that's what we're going to have to do to get the equation I've already shown you. Okay, so Ka times by Kb, we're going to write it down here. So Ka Kb is equal to, let's put it all together, H3O plus A minus over AH, and then AH OH minus over A minus. Sorry about that wonky bracket, but it's fine, isn't it? And then let's do some cancelling. Okay, so the A minuses are going to cancel because A minus, concentration of A minus divided by concentration of A minus is 1. And likewise, the AHs are going to cancel, and that will give us, in a slightly different colour, concentration of H3O plus concentration of OH minus. Yeah, and that is equal to Kw. Okay, now let's just get rid of those actually because I can't see them. The implication of this is that if you have a large Ka, so if Ka is big, then Kb has to be small. Okay, so that means if Ka is big, it means that the equilibrium lies to the right. Okay, so you know that's how we do that. That's what an equilibrium constant means, isn't it? And therefore it means that the equilibrium for Kb is lying to the left. Okay, and it's small. And likewise, if you have a weaker acid with a smaller Ka, it's going to have a stronger conjugate base, a larger Kb. So again, it talks about the position of the equilibrium in both of these situations. Okay, so that's that for now. And yeah, that's the end of this screencast. So thank you very much.